So this video will be about static and dynamic scope, but in order for the video to be interesting, I first need to talk about nested subprograms. Now, on the left, I have a Python program which has a nested subprogram. We're going to see how this program behaves using Python scoping rules. And Python, as most programming languages, uses static scoping. Static scoping means that you can tell which variables are accessible based on the textual layout of the code. Therefore, this is also known as lexical scoping. Now, if we look at this code, we'll see that we have some global variables, and also we have some variables that are local to sub1, and then some additional variables that are local to sub2. However, there are actually some additional variables that are not listed here. You see, in the definition of sub2, A is global, meaning that when we refer to A within sub2, we're referring to the same A that is the global variable A. We also have C. This is declared as a non-local variable. It is not local to sub2 because it is first used in sub1. But because of how it is declared in sub2, whenever I change C, I'm actually changing the value of C declared in sub1. But that leaves some additional variables, B and Y. Now there already exist variables with these names in other scopes. Sub1 has Y and there's a global variable B. But because I did not declare B or Y as being global or non-local respectively inside of sub2, whenever I change those values, I'm actually assigning a value to a brand new local variable whose name shadows the other name in that scope. I can step through the execution of the code and fill these boxes out as we go. First, we assign values of 5 and 10 to A and B respectively. Then we define the functions, and after defining the functions, we make an actual function call. The function call sub145 will assign a value of 45 to the parameter x. Then, inside the body of sub1, we assign values to y and c. Next comes the definition of sub2, and then the actual function call for sub2. The actual parameter of 34 is assigned to the formal parameter z. Then, inside of the body of sub2, we declare A is global and C is non-local. Then, mostly for the sake of space, we have a multiple assignment statement. This just means that each of those variables in order is assigned to the values on the right-hand side of the equal sign, once again in order. Because A is specified as global, the 99 goes here, whereas the value assigned to B goes in the local variable B and not this global variable. C is non-local, so the assignment changes this value here. And then finally, Y goes into the local variable Y and not the version in sub1. At this point, all values have been assigned and we have several print statements. When we print ABC XYZ here, we'll take whichever value is in the deepest scope. So there's only this global value A, so that'll be 99. But B will be 98 because we are currently in sub2, which shadows the global version of B. As for C, the only version we can see is right there. The only X we can see is from sub1. Now, although this is from sub1 and we did not declare it as non-local in sub2, because we're not assigning a value to X, we will display the version of X defined in the parent scope. In contrast, Y will be the local version because we did reassign the value, and Z will be the local version because that's the only option. So this will be printed out from inside of sub2. Sub2 will then return to sub1 and have this next print statement, but because sub2 will no longer exist, meaning its variables no longer exist, the next print statement will be based on these available variable values. So we're going to print A, which is the global A99, B, which is now 10 because the version in sub2 went away. C is still 97, and then X and Y are still the versions in sub1, so 45 and 7. And notice that Y has changed back to its version in sub1, not the version defined in sub2. Next, the call to sub1 returns, and we can only print what's left from these variables. And that final print statement is only printing A and B, and so we simply print 99 and 10. And we can confirm that this is the correct output from running this code by simply running it. And as we see, the output matches what we expect based on the static scoping rules of Python. So if that's what static scope looks like, you may be wondering what dynamic scope looks like. So most modern languages don't really have dynamic scope. Historically, older versions of Lisp did have dynamic scope. Currently, in Common Lisp, the default scope is actually static. But Common Lisp also supports dynamic scope. And so what I'm going to show you are two programs that are identical, except the only difference is the scoping rules. The program we see here is the dynamically scoped program. And all that I changed to make this a statically scoped program is the initial declaration of these variables, like so. Exact same program, except for static behavior, I use setQ, but for dynamic behavior, I have to set up the dynamic variables in advance using def var. So let's see how this behaves. So what does it even mean to be dynamically scoped? Notice that we still have nested subprograms here. In a statically scoped program, if we were to refer to a variable that did not exist inside the current scope, we would look at the text of the program to figure out what the next larger scope is. However, with dynamic scope, we instead look at the function that called the current function. In other words, the sequence of places that we look for a variable, if we can't find it in the current scope, depends on the function call sequence rather than on the textual layout of the code. So let's trace this code with dynamic scope and try to make sense of it. These are the global variables A, B, C, D, and E. Now, at the bottom of the code, it calls big sub, and there is a let command that immediately defines some new variables. If we use a pre-existing variable name on the left-hand side of a pair, we're actually making a brand new variable. So there's a new version of A that equals 2. And there's a new version of B, but the definition of B will depend on these global variables. We're adding D and E to get 90. And then C equals 4. So far, the fact that we're using dynamic scoping has not been an issue, and in fact, a statically scoped program would behave the exact same way. The next thing that happens in the code is that functions sub1 and sub2 are defined inside of big sub, and then after that, these functions are called. Sub2 is called first, and it defines new variables D and E. D is defined as B plus C, and those will be the versions of B and C inside of big sub. So this will equal 94. E is defined as 2 times A. That will also draw on the value from big sub, so we get 2 times 2 is 4. Once again, this is so far not different from static scoping, because sub2 is textually defined inside of big sub. But the reason that the dynamic scoping is behaving the same here is that we also happen to call sub2 from big sub. Inside of sub2, we define and then immediately call sub3. This introduces more variables. We have a equal to e plus c, and we're using dynamic scoping, so we will go up the call sequence, this version of e plus that version of c, so 4 plus 4 equals 8, and then b is 2 times d, and going up the call sequence we get 94, and so 2 times 94 is 188. Interestingly, we still haven't done anything with the fact that we're using dynamic scoping, but we're about to call sub1 from inside of sub3, and that's where things get interesting. Sub1 introduces the variables d and c. D is defined as a plus b, so we look up and see that there is an a here and a b here, so the 8 plus the 188 equals 196. The c is defined as 2 times e, and so that'll be 2 times this e, which is 4, so 8. What's important to note here is that because we're using dynamic scoping, sub1 got the values of a and b from sub3, which called it, even though in the text of the program, sub1 is not defined inside of sub3. The format command that comes at this point in the code will print out the values of several variables, and we'll see which values are displayed. To find each value, we start down here and then look up for the nearest value with that label. So A will be 8, B will be 188, C is 8, D is 196, and E is 4. We can confirm this output is correct by simply running the program. And we see that the first line of output matches what is written here. The second line of output is produced by the other call to sub1, which occurs here. Now, I'll leave tracing that as an exercise for you, but basically, this second call also doesn't take advantage of the fact that we're using dynamic scope, because when you call sub1 directly from inside of big sub, you are calling a function from inside of the function it is statically defined inside of. So you get the same behavior as with static scoping. Only the first line of output really takes advantage of the dynamic scoping. So next, I'll show what happens to these values if static scoping is used instead. In the statically scoped version of the code, everything is the same up until we call sub1 from inside of sub3. Once we execute sub1, we have to define these variables d and c. But now we're going to look in the surrounding scope for the values of a, b, and e. The scope that textually surrounds sub1 is big sub, and then the global variables. Everything in sub2 and sub3 is textually separate from the scope where sub1 is defined. So when we want to compute the value of d, and we're adding a and b, we have to first look to big sub, and we see that there is indeed a value named a and a value named b inside of big sub. So b plus a is 92, and that goes here. And then c is 2 times e. Well, once again, we look at big sub first, but there is no e here. So the next place we look is the global values, where e is 50. So 2 times 50 is 100. That means when we print out these values, d will be 92, and c will be 100. And we also have to figure out what these other values will be. And of course, I just said that the reason that d equals 92 is because we added these values of a and b. So a here will be 2, and the b will be 90, and the e is 50. And we'll confirm these values by running the code. So here's the result of running the static code. And for the sake of comparison, we'll run the dynamic code as well. As was stated earlier, the second line of output, which I have not traced, doesn't actually depend on dynamic scoping at all. And so that's why in both the static and the dynamic versions of it, the second line of output's the same. But we can see that the first line of output from the statically scoped program does match the output we traced out earlier, shown here once again for comparison. Before I wrap up this video, I'm going to show you one more thing that demonstrates how the scope rules are actually implemented. So this diagram is, once again, a call stack full of activation records. However, for the sake of space, I've compressed it a bit. Rather than showing each individual variable as a separate entry in the stack, I've simply taken all variables and listed them in a single row, but I have added some additional fields to each activation record, which I did not show you before. These are the dynamic link and the static link. Now, we did have the return statements before, or specifically the return addresses. And so this stack is meant to demonstrate what the call stack looks like at the point we just had in the video, which is right before the format command that printed the values of the variables. Now, as was stated previously, most of the variable values are the same in both the dynamic and statically scoped versions of this code. It's only at the very end inside of sub1 where we get different values. And I'll show you how the executing program figures out how to find these values using the static and dynamic links. We'll be doing the dynamic links in green, and basically every dynamic link points to the base of the activation record that called it. So this dynamic link would point to the base of the global activation record here. And then this dynamic link would point to the base of big sub. And this dynamic link would point to the base of sub 2. And then the dynamic link here points to the base of sub 3. So once again, a dynamic link points to the base of the activation record of the function or subprogram that called the next subprogram. So sub 3 calls sub 1, so sub 1's dynamic link points to the base of sub 3. Sub 2 called sub 3, so sub 3's dynamic link points to the base of sub 2. Now, the reason this is useful is that if I want to figure out what D and C are, and remember how we define these, D equals A plus B and C equals 2 times E. So if I want to look up the values of A and B, and I can't find them here, then I follow the dynamic link if I'm using dynamic scoping. So I follow the dynamic link to this activation record for sub 3, and I look inside of it for A and B, the values I'm looking for. And sure enough, I find those values, so I then fill them in, compute the value of D, and I get 196. And then for C, I need the value of E, so I follow this link, look inside of this activation record. There is no variable E here, so I then follow that dynamic link to the activation record for sub 2. I look inside of this activation record, and there's a value of E. So I take that value of E, plug it into there. 2 times 4 is 8. Now, the red will represent the static scoping. The static links point to the base of the activation record for the function within which a given function is textually located. So big sub is a top-level function that's in the global scope. So its static link points to the base of the global scope. But then sub2 is defined inside of big sub. So sub2's static link points to the base of big sub. The fact that these static links are pointing to the same places as the dynamic links explains why, up to this point at least, in the call stack, there is no difference between the static and the dynamic scoping. And that trend continues with sub3, because sub3 is defined inside of sub2. So sub3's static link points to the base of sub2. And then finally we get to the interesting case. Sub1 is statically, textually defined inside of big sub. So the static link for sub1 actually points to the base of big sub. And that explains why when sub1 is looking for values A and B and E, it follows this static link when it's using static scoping, and it goes all the way down to big sub, looks inside of this activation record, and finds the values 2 for A and 90 for B, so you end up with 92 here. And then for C, we need the value of E. Well, the static link went to big sub. There is no E here, so we then follow this static link to the global scope and find E equals 50, and then we multiply that by 2 to get 100. So this diagram shows how the static and the dynamic links allow implementation of either static or dynamic scope with essentially the same framework, just a slight tweak in where you look for the variables during runtime within the call stack.